based on electrical circuit which was given, and I hope you would have solved that question. So see this question you have went through this, I hope, and this is also given in the notes. You can go through this and try to solve this question and try to find the answer. Okay. Now move to the that another topic which is called state transition matrix. Okay, so state transition matrix basically gives you basically works on the solution of homogeneous state equation. So homogeneous state equation means input is zero, that is u of t should be zero. So basically works state transition matrix only works for when the input is zero. Okay, so that is input is zero means that it will have a homogeneous equation, and that x dot of t is equal to ax of t and plus bu of t. So we have a state model equation and we substitute u of t is equal to 0. So we'll get x dot of t is equal to ax of t. So now you can see if we take a Laplace transform on both side, so x dot of t can be written as s x of s minus x of 0. So see in this y we have taken x of 0 here. So see there will be an initial condition. Okay, so we are just considering initial condition. So initial condition means if you have a dx upon dt, okay, if x is having x of 0 is there, okay, x of 0 is there, that means initial condition if present, okay, x of 0 is not equal to 0, so initial condition is present. So if you take it in a Laplace transform, so that will give you s x of s x of s minus x of 0. I hope you all of you have done in a electrical circuit or network theory in a Laplace transform. So while representing electrical circuit like inductor or capacitor in the form of Laplace circuitry or Laplace equation, so you can go through this. This is the form of dx by dt is equal to sx of s minus x of 0. Simply we represent if sx of s if initial condition is 0. So you would have seen that in transfer function equation we have taken that sx of s everywhere, because in that transfer function we assume that initial condition is 0. Okay, so here initial condition is not 0, so sx of s minus x of 0 is equal to ax of s. Okay, so now if you take x of s this side, so this will become sx of s minus ax of s is equal to x of 0. So x of 0 will come this side. So now this is the equation number 1. Okay, this is equation number 1. Now let us consider analogous scalar equation. So we just substitute a vector this is a vector matrix, and this is basically analogous form of scalar form. Okay, so we just assume that this a can be represented in a scalar. We represent as a form. Okay, a, so this will become s minus a into x of s is equal to x of 0. So x of s become x of 0 divided by s minus a. Okay, and if we invert if we take inverse Laplace transform, so this will give you x of t is equal to e to the power at x of 0. So already you know 1 by s minus a is equal to e to the power at in a Laplace transform. Okay, so okay, inverse Laplace transform. So in inverse Laplace transform, you can have 1 by s minus a is equal to e to the power at, and this is x of 0 will give you same, it is a constant value, so this will give you x of 0 because it is an initial condition that will be fixed. Now the equation number 1, the solution of equation number 1 can be written as this is equation number 1. So this solution of this equation is nothing but this equation, x of t is equal to e to the power at x of 0. So now we have taken the for solving purpose we have taken just analogous form, and that is in a scalar, because if you not take a scalar form will have very difficult to solve. Otherwise we can go through this, but it will be difficult to have a matrix representation in an inverse Laplace transform. So just we can replace this a by again this a by capital A. This is a matrix, so scalar to vector we just represent. So we can have x of t is equal to e to the power capital AT x of 0. Okay, this is e to the power at is nothing but phi of t, which is called STM, state transition matrix. So just remember this e to the power at is equal to phi of t, which is equal to a state transition matrix. This is this will be useful. Okay, this will be useful for us. So e to the power at is equal to phi of t, which is equal to state transition matrix. So if we multiply state transition matrix with the initial condition, we'll get x of t condition. Okay. Now what is e to the power at? E to the power at, or simple e to the power at can be written as in a equation form. So we'll have 1 plus at plus a square t square by 2 factorial plus a cube t cube divided by 3 factorial dot 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 dot. We can go through the up to a to the power n t to the power n divided by n factorial. So if you simply represent a scalar with the vector a, and here also a scalar with the vector a, you just represent here and you will get e to the power at is equal to I. Why I is written? Because we are basically dealing with we are dealing with vector quantity. So a is a vector quantity, a is a matrix. So vector we can say matrix, okay, matrix form, and this is also matrix, this is also matrix, so this is also matrix. So if you take a is a matrix and a to the power 3, so you just multiply matrix into matrix into matrix, okay, 3 times a into a into a. So always give you the matrix which is having a dimension of if it is a square matrix, so a to the power 3 matrix, so that will give you suppose a is a n matrix, n cross n matrix, so that will give you n cross n representation. So simply you take n cross n identity matrix to add one, because one we cannot add to the matrix, okay. So we should have take that identity matrix in the addition. So if you represent this in a summation form, so this summation will be represented from I equal to 0 to n and ai to the power I t to the power I and I factorial, okay. So you can, if you want, you can take simply a to the power I t to the power I divided by I factorial, not ai is same as a, okay. So you can have a to the power I t to the power I divided by t to the power I divided by I factorial, or if you want you can represent in a k form also. So you can have k is equal to 0 to n, k is equal to 0 to n, a to the power k t to the power k divided by k factorial. You can write any form, okay, I k n, any form, okay. So this is your exponential term e to the power at, and whenever e to the power at we will try to find, okay, we'll represent in this form, okay, and we'll go into the question, we'll check how we can find a state transition matrix. So, okay. So now move to the another part, which is called properties of state transition matrix. Before going to the properties of state transition matrix, try to find phi of s. So we have phi of t. Phi of t is equal to basically phi of t is equal to, we can write Laplace inverse of phi of s. So because phi of s was written as si minus phi of s is equal to written as what was that phi of s? Phi of s you can see here. Phi of t is equal to e to the power at. Phi of t is equal to e to the power at. So if you represent phi of s, so you can see here phi of s is nothing but c. Where is my cursor? Okay. So now see, if you represent this, you can write 1 upon, if you write in a matrix form, 1 minus 1 divided by s minus a, or si minus a. We cannot directly s minus a, we cannot write. We should write si minus a, because a is a matrix form, so it is having n cross n dimension, so we should have multiply n cross n. So 1 upon si minus a x of 0, if we write in a matrix form, so this can be written as si minus a inverse x of 0. So x of 0. So this si minus a inverse is nothing but this is e to the power at, which is called phi of t, phi of s. Okay, phi of s. So this is simply, that's why it is written as this is simply written as Laplace inverse of si minus a inverse. I hope you understand, you understood this. Okay, this is si minus a inverse, Laplace inverse of si minus a inverse. So you can write phi of t as phi of t in a t form. Phi of t is written as e to the power at, and in a Laplace form you can write phi of s is equal to si minus a inverse. Si minus a inverse you can write here. Okay, this is called a state transition matrix, and there are some properties of a state transition matrix. We will go through one by one, and this can be asked for 2 marks. You can go through this. Okay, this is very simple. This can be asked for competitive examination directly. It is asked in a competitive examination. Properties directly asked in a competitive examination. So you can go through this. So see, it is written as properties of a state transition for time invariant system. X dot of t is equal to ax of t. Okay, and phi of t is equal to e to the power at. So if we have phi of t is equal to e to the power at, we can simply represent phi of 0. If we try to find phi of 0, we will represent e to the power a into 0. So e to the power a into 0 means we'll give 1. And here, because a is written, that's why we should write identity matrix, because it will give you the identity, it will give you the matrix form. So this will give you identity matrix for n cross n. Suppose a is n cross n dimension, so identity should be n cross n dimension. Okay, so phi of 0 is equal to identity matrix. So you should remember this, phi of 0 is equal to identity matrix, because it is equal to e to the power a into 0. Now we have phi of t is equal to e to the power at, and if we have phi of minus t, if we try to find, so we can have phi of minus t. So simply, if you want to represent phi of minus t, you can go through phi of minus t also. But here, if we take minus sign here, in A we take minus sign. So this will be give you minus sign here. And if you try to take a power of minus 1, so this minus minus will cancel, will give you same e to the power at. So now if you have phi of minus t, what will happen? Sorry, phi of minus t, what will happen? We have phi of t is equal to e to the power at. Phi of t is equal to e to the power at. If you take, instead of t, if you take minus t, so you'll have right phi of t is equal to e to the power minus at. So see here, we have written e to the power at as e to the power minus at to the power minus 1. So this will give you same value e to the power at. So what we'll write, is e to the power minus at as phi of minus t, phi of minus t to the power minus 1. So that means if you write in terms of phi of t, in terms of phi of minus t, you should take a inverse of that. You take a inverse of that. So phi of t is written as phi of minus t to the inverse. Okay. So this is the one property. Okay. And if you write in another form, you can write also this as a phi inverse of t as a phi of minus t. You can write phi inverse of t as phi of minus t. See, I have taken inverse on the both side. I can take inverse of both sides. So we'll take another properties will form. So if you take inverse of both sides, so phi inverse of t can be written as phi of minus t of inverse of inverse. So inverse get cancel. So this can be written as phi of minus t. So phi inverse of t is equal to phi of minus t. See, this property can be used, and it can be written as phi to the power nt. Phi to the power nt is written as phi nt, phi n of t. So that's why it is written as phi t to the power phi t to the power n. It is a power of n, or phi n to the power t, phi to the power n function of t. So it can be written as phi nts. Whatever thing will be there, you just multiply with the time. Okay. So that is the property it is given here. So I hope you understood this. Phi t n is equal to phi nt. Now we have phi t1 plus t2. It can be written as phi t1 dot phi t2. Okay, phi t1 dot phi t2. So you can have phi t1 plus phi t2. So just you just have a quick proof. So phi t1 plus t2 can be written as t1 plus t2 can be written as e to the power e to the power a t1 plus t2. So you can have e to the power a t1, okay, plus a t2, you can write in the power also. So if you have e to the power a plus e to the power b, so you know the property e to the power a plus b can be written as e to the power a into sorry e to the power a into e to the power b. You can write base is same, power will be written over there. So e to the power a t1, okay, into e to the power a t2 you can write. So what is e to the power a t1? It is nothing but phi t1, and it is nothing but phi t2. This is the proof of this property. So phi t1 plus t2 is written as phi t1 plus phi t2. If we have phi t1 minus t2, we can write phi t1, okay, phi of t1 into phi of minus t2. Okay, so simply you can write here. Now we have phi t2 minus t1. So how we can write phi t2 minus t1? See, t2 minus t1 can be written as phi t2 minus t1 can be written as, okay, it is not phi t2 minus t1, phi t2 minus t1 into phi t1 minus t2. So if you have this form, you can write, okay, you can write here. So see here, we are just having a t1 minus t2 minus t1 and into t1 minus t2. So this t1 get cancelled if you take in exponential form. So t1 get cancelled. This can be written as t2 minus t0. So this can be written as phi t2 minus t0. Okay, phi t2 minus t0 it can be written as. So this is wrong. This is not like that. Okay. So this can be written as t2 minus t0. See, this is also having simple proof. You can go through this. See, we are writing e to the power t2 minus t1 into a, okay, and into e to the power a t1 minus t0. So if you take power addition, so you will have a t2 minus t1, okay, plus t1 minus t0. So this t1 get cancelled. You will have e to the power a t2 minus t0. So simply if you want to represent, you can write phi of t2 minus t0. So that's what it is written here. It is nothing but phi t2 minus t naught. Okay. Okay, I hope it is clear. Now if you have phi t1 minus t2 minus t2, and this is t2 minus t naught, so you will have t1 minus t naught. Okay, so you can simply represent. So you can simply substitute all these in equation, and you can go through this and try to verify all these property. Okay, so I hope these properties are understood with you, understood to you. Okay, so you can go through this and you can have a simply quick proof. Okay, you can go through the proof also. Now these properties can be used in the while solving some problems, and we'll use these property. Okay, while solving the problem. Okay, so now the another topic which is given a solution of non-homogeneous state equation. So how we can go through the non-homogeneous state equation? So see, this is the non-homogeneous state equation is given, and in the non-homogeneous state equation is given, we have u of t is not equal to 0 for non-homogeneous equation, and we have taken the initial condition at t is equal to 0. So there it was taken as a homogeneous equation. So homogeneous equation, for homogeneous equation u of t is equal to 0. So input was 0. Now we are taking non-homogeneous equation. So in the non-homogeneous equation u of t is not equal to 0. So input is not equal to 0. So now we have two cases. The first cases will be without initial condition. Sorry, the first cases will be with initial condition, and the second cases will be without initial condition. So if the input is there, we'll have initial condition or will not have initial condition. Both the condition will be applicable. So first condition is without initial condition, sorry, with initial condition. So we have a state model equation x dot of t is equal to ax of t plus bu of t. So now if we take in an analogous form or a scalar form, we can write x dot of t is equal to ax of t plus bu of t, and a and b are taken as a scalar. So simply we can solve this, and after solving we can write directly as a scalar to matrix form. So taking Laplace transform, will have sx of s minus x of 0, which is equal to ax of s plus bu of s. So you can say, okay, sir, why you have not taken instead of while taking x of t as x of s, why you have not taken x of 0 here? We cannot take x of 0 because in x dot of t only initial condition will be taken care, because x dot of t is nothing but dx of t divided by dt. So if we take Laplace transform of this can be written as sx of s minus sx of s minus x of 0. So this is simply basically this is simply representation of x of t with x of s. So Laplace, simply Laplace, and this is basically differential of Laplace. So we should have take initial condition. If initial condition is not there, the story will be different. So we'll see the story. The second point we'll go through the without initial condition. So we can simply go through this, and this is x of s minus ax of s, which is equal to x of 0 plus bu of s. So we can take s minus a as a common, so x of s will be written, and this can be written as x of 0 plus bu of s. So x of s can be written as s minus a inverse x of 0 plus s minus a inverse bu of s. Okay, so this is simply representation. See, you can also say, sir, why you have not taken b into s minus a inverse? See, this is basically just a representation. We are taking the analogy between a scalar to the matrix form. So you should write in a proper order, because s minus a is a left hand side. So left hand side of this equation, all these equation, left hand side s minus a inverse will be multiplied, not in between, not in right hand side. Otherwise we'll have the matrix dimension error. Okay, so we should not match the matrix dimension. Okay, so in the matrix multiplication, dimension should match. Okay, so if we multiply s minus a inverse in between, so see, in scalar it will not be any problem, but in matrix representation it will be very hectic to solve. It will be very difficult to solve that particular matrix dimension. Okay, so you can just multiply it in the left hand side, because left hand side s minus a is there, so just multiply. Okay, so now we can simply represent, we can simply take inverse Laplace transform. So inverse Laplace transform can be represented as x of t is equal to e to the power at x of 0 plus l minus Laplace inverse of s minus a inverse bu of s. And this Laplace inverse of s minus a bu of s can be written in this form. So this minus s minus a inverse is basically represented in the form of g of s. Okay, So it is a simply representation. Okay, so S minus A inverse into B is represented as G of S, and we'll try to take in a Laplace transform. So see, Laplace inverse can be is written as Laplace inverse of G of S into F of S. So both multiplication. So we'll have Laplace inverse of G of S into F of S. So just multiplication will have 0 to t G of t minus tau, okay, f of tau into d tau, okay, and this b is associated with the b is a basically constant value, so this is associated with the g of s, so it is associated with the g of t. Okay, if you don't want to write, you can go through, you can take b as a outside, okay, b as a outside, and you take b later stage. Okay, so this is b is a constant, so we are not focusing on that because this is in a function of s, and this is also in a function of s. So we just try to take Laplace inverse. So how we can write the Laplace inverse? So this Laplace inverse can be written gt minus tau, f of tau, and d tau. Okay. So now we can simply represent x of t as this equation. So x of t is nothing but e to the power at x of 0. And how this e to the power at x of 0 is written? So from this equation. So this c s minus a inverse x of 0. So if you take Laplace inverse of this can be written as x of t is nothing but x of 0 is nothing but is a constant value. This will give you x of 0, and this s minus a inverse means 1 by s minus a. 1 by s minus a is what? 1 by s minus a is what we'll get. So we'll get s minus a inverse is nothing but e to the power at. So you can simply represent e to the power at, okay, e to the power at x of 0. Okay, now this can be simply represented as b you take outside. So b we have taken e to the power a t minus tau and u tau. Why e to the power a is taken outside? Because here it is taken as a and minus a tau. Okay, so and u of tau is already there. So you can simply represent this, and you can take the analogy, and you just replace a with the capital A, and you will have x of t is equal to e to the power at x of 0, 0 to t e to the power a t minus tau b u of tau d tau. So this is equation number 1, and if you take in a phi of t representation, so you can have e to the power at as phi of t, and e to the power at minus tau is a delayed function, so it is written as phi of t minus tau and b u of tau. B can be written as capital B. Okay, so again for the matrix matrix basically matrix dimension matching with the matrix dimension, so we should multiply b here. Okay, otherwise our matrix will not be matched. Okay, so if you can take b anywhere but in a scalar, but in a matrix representation you should match with the your outcome value. So x of t should be in the dimension of n rows and 1 column, so this should be in a n cross 1 matrix, and this should also give you overall, this should give you n cross 1 matrix. So you'll have this n cross 1 matrix representation, so you can go through this. Okay, now this equation you just remember, so how we can find the initial condition using the initial condition, and for the non-homogeneous state equation, non-homogeneous equation we can find, and a state transition matrix again it will be e to the power at. So this is basically the output. This is basically the equation given for solution for non-homogeneous equation, and this is the solution. You can go through this, and while solving the problem, will be in problem it will be asked that find the non-homogeneous solution. Find non-homogeneous state or solution or non-homogeneous solution for the given state transition matrix or given state model equation. We'll go through the problem also, and we'll try to recall these formulas, and we'll try to solve using this. Okay, now if for t is equal to t naught, initial time is given for t is equal to t naught. Okay, so then what will happen? So we'll try to take the equation 1, and we'll try to use. Okay, so x of t naught for initial time t naught, it is given as, so x of t naught, if you substitute t is equal to t naught, you just put it into the equation. So this is t naught, t is equal to t naught, so this will give you e to the power a t naught x of 0, 0 to t e to the power a t naught minus tau b u of tau d tau. Multiply e to the power minus a t naught with both the side. So just e to the power minus a t naught with both the side, you will get x of 0 as this equation. So you can find x of 0 as this equation. Substitute x of 0 in this equation and try to solve, and you will get this type of equation, x of t as this type of equation. Okay, so this is the equation for x of t when initial time is given. If initial time is not given, you should take simply as a t is equal to 0. Okay, initial time. Okay, so if initial time is given, your equation will be changed and this equation will be there for the initial time. Okay. So you can again rearrange that equation and see e to the power a t minus t naught x of t naught. Okay, e to the power a t minus t naught x of t naught, and this is minus 0 to t. Okay, 0 to t naught 8 e to the power a t minus t minus tau b tau and d tau. Okay, so this simply it is written, and you can have this e to the power a to the power a t minus t naught. Okay, 1 minute. Okay, e to the power a t minus t naught x of t naught. Okay, and plus t naught to t. So we'll have some. See, this is the inside. क्या कहते हैं, inside integration both are same, so you can have a simple a simple properties of integration. You can have a to b, suppose this is x of t dt. Okay, and plus b to c x of t dt. So inside the integration both are same, so you can have a to, you can have directly, you can write directly a to c x of t dt. You can simply represent. Okay, so this is the property of integration. So just we use the integration property. So we are taking t naught to 0 and 0 to t, 0 to t. So we can simply write t naught to t. So this is written as t naught to t, or whatever the thing inside the integration, just write right here. So in the form of phi of t, how we can write? We can write e to the power a t minus t naught x of t naught as a phi of t minus t naught, and this is already x of t naught, and this is t naught to t. This e to the power a t naught b u of t can be written as, so e to the power a t naught can be t minus tau, can be written as phi of t minus tau. This is a delayed function. So phi of t minus tau b u of tau. So this can be written as this can be written as a zero state response. This is called zero state response, and this is called zero input response. And if you add the zero input response and the zero state response, your x of t will give you the overall response. Okay, overall response. So this is called overall response. Overall response. Okay, so this is overall response. Okay, so overall response will be addition of zero input response and zero state response. Zero input response means you are not applying any input. See, this is the term, in this term, this is independent of any input, independent of input. So u of t is not there, independent of input. Okay, zero state response means independent of initial condition. Independent of initial condition, there is no initial condition at all. So it is independent of okay, independent of initial condition, and this is independent of input. So if you add all these zero input response and zero state response, you'll get overall response. Overall response should be combination of these two. So till now we went through a state transition matrix, and we found out how a state transition matrix can be represented, and we saw that e to the power at is the state transition matrix, and e to the power at can be represented as phi of t. Phi of t is a state transition matrix, and e to the power at can be written as I plus at plus a square t square by 2 factorial. It is like e to the power x e to the power x expansion. Okay, e to the power x can be written as 1 plus x square by 2 factorial plus x to the power 3 by 3 factorial plus dot 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 x to the power n by n factorial. So it is simply representation. We went through the scalar, and we just converted into matrix form, and we just represented the state transition matrix. Now we went to this properties of state transition matrix. So there are few properties. So this property you just remember, and you try to validate, to try to verify this state transition matrix properties using the state transition matrix formula, and you can try to validate. Okay, now we went through the solution of non-homogeneous equation. So non-homogeneous equation means previously we went through the homogeneous equation. So this is the solution of homogeneous equation, and you can simply say what is the solution? Solution was this: x of t is equal to e to the power at x of 0. So this is the solution of homogeneous equation. If we have homogeneous equation, this is the solution: x of t is equal to e to the power at x of 0. This is equation number 2 or equation number 3. You can have this, So this x of t is a solution of homogeneous state equation. So if you are asked to find homogeneous solution or homogeneous solution of homogeneous state equation, you should find x of t as e to the power at into x of 0. You just multiply, you just find a state transition matrix and just multiply it with the x of 0, you will get same, you will get x of t. Okay, so now we went through the solution of non-homogeneous state equation. So in the non-homogeneous state equation, we went through the initial condition at t is equal to 0, and we found out for the initial condition at t is equal to 0, and for initial condition, if it is taken as initial condition t is equal to t naught. So for the initial condition t is equal to t naught, we try to find, and we have got the equation. Okay, okay, I hope it is correct. ठीक है. Okay, so now try to see the problem, and the problem which is given as find state transition matrix for the state model given by A is equal to this. So see, it is not given as state model, it is given as a okay, state model or a state matrix. It is given as a state matrix, a state vector matrix or a state matrix. It is simply written as. So A is given. So using the A, you try to find a state transition matrix. So to have a state transition matrix, what should be the state transition matrix formula? Phi of phi of t should be, or phi of s is equal to, we know phi of s is equal to e to the power e to the power, sorry, phi of t is equal to e to the power at, and phi of s is equal to, we know phi of s is equal to si minus a inverse, si minus a inverse. If you take inverse Laplace transform, so take Laplace inverse of phi of s, which is equal to phi of t, which is represented as Laplace inverse of si minus a, okay, inverse. So you just try to find, first of all, try to find si minus a inverse, and then you take a Laplace inverse of that. So to have Laplace inverse of si minus a inverse, so we should try to find si minus a inverse. So to have si minus a inverse, we'll go through si minus a. So we have a matrix which is given here, and we'll try to find si minus a. So it is directly written, you can go through the step by step. It is written as si minus a. So we have a is given here, si means it is written as si directly. I'll write here. I hope you understood this. Sorry, this is 0, this is s. So this is si. See why si is taken as 2 cross 2, because a is a 2 cross 2. To have a compatibility, we should write si as a 2 cross 2 matrix. So s is multiplied with the identity matrix. So this is simply 0. Okay, this is s, this is 0, this is 0, this is s, and we have minus 0, okay, minus 1, 2, minus 3. So this can be written as s minus 0 as s, okay, and minus 1 into minus it is written as a plus 1, and 2 is written as a minus sign, so this is written minus, okay, and this can be written as s minus of minus 3 is s plus 3. So you just take inverse of this. So to have Laplace inverse of this, we'll try to first of all we'll try to find the adjoint, and after finding the adjoint, we'll take determinant, divide by determinant. So inverse may 2 cross 2 directly you can find the inverse. You just interchange these two, and try to multiply with these two as a minus sign. So just it is taken as s plus 3. S is interchanged, and it is written as a minus sign is multiplied here. You can see here minus sign is multiplied here, and this is also multiplied with the minus sign. And what should be the inverse? Inverse should be 1 upon determinant of si minus a. Determinant, it is not written, so 1 upon determinant of si minus a. So what should be determinant? So see here, it is written as adjoint of si minus a and divide by determinant of si minus a. So what should be the adjoint? Adjoint is this one. What should be determinant? Determinant of that one, not adjoint wala determinant. Determinant of this matrix. You should find determinant of this matrix. So what should be s into s plus 3, s into s plus 3 minus of minus 2. So plus. So s into s plus 3 plus 2. So it is written as s into s plus 3 plus 2. Okay. So s into s plus 3 plus 2. So it will be s square plus 3s plus 2. So s square plus 3s plus 2. It is multiplied with all the element. So it is written as s plus 3 divided by s square plus 3s plus 2. It is a minus 1 divided by s square plus 3s plus 2. It is 2 divided by s square plus 3s plus 2. S divided by s square plus 3s plus 2. Now this is basically, this is still si minus a inverse, not the solution. This is si minus a inverse only. Now what is phi of t? Phi of t is nothing but Laplace inverse of this. So Laplace inverse of this matrix means Laplace inverse of this individual. this individual Laplace inverse you try to find. Okay, this problem is not so easy. Okay, see, the question is one liner question, only one line it is given, but you need to solve all these. Okay, so to have a Laplace inverse, I hope you are all are familiar with this, and I don't want to go through in a Laplace inverse how you find the Laplace, but in a quick revision, I'll tell you how you can find. But in the next problem, from the next problem onwards, you try to find by your own. Okay. So s plus 3 divided by s plus 1 into s plus 2. So try to find this. You just split a divided by s plus 1, b divided by s plus 2. So I have written a divided by s plus 1, b divided by s plus 2. So by using, we can write a divided by s plus 1. So a divided by s plus 1 and b divided by s plus 2 can be written as s plus 3 divided by s plus 1 into s plus 2. Okay, whatever the method you know, you just go through this, not my method. Okay, you go through any method, but answer should be same. So you can have s plus 3 as a equation. I'll write. So we can have s plus 3 as a into s plus 2. Okay, a into s plus 2 plus b into s plus 1. So this is simply written, and denominator will be cancelled out. So if you take substitute s as a minus 1, so this can be written as minus 1 s a into s minus 1 plus 2. So it is written as a 0. So the b as a minus 1 you are writing now. So minus 1 means what? It will be 0. So this can be written as, what will be this? This can be written as s as a minus 1. I'll try to, sorry, this is 2 now. So to have, okay, to have a value, we'll write s equal to minus 1. I'll try to write s equal to minus 1. So what will happen? S equal to minus 1, if we substitute, put s equal to minus 1. So this can be written as plus 2, which is 2 is equal to, what will happen? 2 is equal to a, okay, plus 0. So a is directly, a is equal to 2. A is equal to 2, which is the answer. This is one type of solution which is written as a is equal to 2. Directly it is a equal to 2. Now you put s equal to minus 2. Okay. So s equal to minus 2, if you substitute, a term will be 0. So you can write minus 2 substitute here. So this will give you 1. 1 is equal to b into minus 2 plus 1. What will happen? This will be 1 is equal to b as what value? This is minus 1 now. This is minus 1. So this is minus b. So b is written as minus 1. B is written as minus 1. Okay. So this is simply minus 1. Okay. What happened? I hope this is basically, this is wrong. This is wrong. This should be minus 1. This should be minus 1. It is not written here. If a is equal to 2, b is equal to minus 1. Na? You see the equation. A is equal to 2, 2 minus 1 is equal to 1. Na? So this should be minus 1. Okay, यहाँ पे लिखा है इसने, but यहाँ नहीं लिखा. ठीक है. So b should be minus 1. So this is one type of solving method. You can have another method, and you can try to solve using the another method also. Try to find the solution. Okay. So I hope this is good. You can go through another method also, but I'll prefer this method. Okay, I'll prefer this method. So again, I'll tell you for another thing. So if you want to write directly, you can go through this, and you just write 2 is a numerator. What is this? I'm writing for this one. So what is in the numerator? It is written as a 2. So I'll write 2 here in the left hand side, and in the right hand side, I'll try to write, we have split it 2 terms. So I'll try to write a into s plus 2, a into s plus 2, second term. For a, second term will be multiplied, and the b for the first term will be multiplied, plus b s plus 1. And try to put s value, different s value. By 2 value you can substitute, c, b with b, it is multiplied with s plus 1. So just multiply the minus 1. So b put s equal to, one time you put s equal to minus 1, and try to find the value s equal to minus 1, and another time put s equal to minus 2. Why minus 1? Because here if you equate with the 0, it will give you s equal to minus 1, and here if you equate with the 0, it will give you s equal to minus 2. So try to put s equal to minus 1 and s equal to minus 2, and try to find a and b value, and put it into this. Okay, and you can have splitted term. So after that you can find the individual Laplace. So if you have Laplace inverse of, if you have Laplace inverse of A minus B, okay, so you can write simply as a Laplace inverse of A minus Laplace inverse of B. You can write this is a property of Laplace, so you can find individual Laplace and try to find. So this is the thing. So what is the Laplace of 2 divided by s plus 1? So it is written as 2 e to the power minus t, and it is a minus e to the power 2t minus 2t. So that's why it is written as 2 e to the power minus t plus e to the power minus 2t. So this is what the solution, which is x of t, which is written here. Okay, sorry, phi of t, which is written here. Okay, I hope this is good. I hope this you understood. थोड़ा बहुत समझ में आया होगा. Okay.
Yes, sir.
Okay. Very good. So I'll try to take another problem and I'll. Okay, time up हो गया ना?
Yes,
Okay,
sir.
what is your next class? Which is your next class?
EMI, sir.
Next class.
EMI.
Huh?
EMI.
EMI. Okay,
EMI.
okay. Okay, no problem. Okay, we'll see you tomorrow's class. Okay. So we'll go through the time response
Yes,
of
sir.
a system, okay, which is described by the equation, and this equation is given. You can take this equation and try to solve by your own. Okay, try to solve. You try to write this equation, try to solve. Write this problem and try to solve. We'll see this problem in the next class. We'll go through. We'll go very quick. So try to write this problem and go through this. To go through the solution. In tomorrow's class, I'll go very quick because we have many problems to solve. So write this problem. Try to solve by your own. Okay, and then we'll match with this equation. We'll match with the solution. Okay. Till now, any doubt? Any doubt? Let me take the attendance, then you can leave. Any doubt? I hope all of you have written this problem. Or shall I wait? I hope all of you have went through this problem. You have written this in your notebook.
Yes, sir.
Okay. So let me take the attendance and then you can leave. Okay.